Here's 13, letter D, maybe possibly E. We'll see how much time we have here. It is a limiting reactant question here. So you have 57 grams of octane, that with 224 liters of oxygen. So that's how much is available at STP, and then determine limiting reactant. So let's turn these 57 grams of octane into moles, and octane is 114 for a mole. So divide this by 114, ends up being a half a mole. So this right there is 0.5 moles. So 0.5 moles of octane. And 224 liters, since we are at STP, we can divide this by 22.4. So we have 10 moles of oxygen. So we have a half a mole and 10 moles. Well, that means this is 20 times bigger than that. And it only needs to be about 12 and a half times bigger. So we have excess oxygen. Limiting reactant is the C8H18. So we know we're going to use all 0.5 moles of that. There's going to be excess of that. Number 2 there, how many liters of carbon dioxide would be produced? So just start with your limiting reactant. So any stoichiometry you want to do, start with your limiting reactant. You can't start with 10 moles because you have excess of that. But I can say we have 0.5 moles of C8H18. Ratio is for every 2 moles of C8H18. Trying to get to carbon dioxide, there's 16 moles of CO2. If we wanted moles, we stop right there. It wants to know liters. Since we're at STP, we can say every mole of CO2 is 22.4 liters. Mole of any gas at STP is that. So 89.6 liters of CO2 could be made. How much of the excess reactant would be left over after the reaction is complete? Since it is since it is oxygen, we need to tell our answer in liters. Okay, so how much excess is that? Well, let's figure out how much oxygen would be used. Let's figure out how much of the liters would be used. Okay, we could do a little ice table. Sorry, I called initial change it BCA table for you guys. You'll eventually call it ice tables. Or we can just do a little strike and say, okay, we know we're using 0.5 moles of C8H18. And for every 2 moles of C8H18 that we use 25 moles of O2. So if we do our mole ratio there, that would tell us how many moles of oxygen were used. We could subtract from our 10 moles we had available. Actually, I'm just going to keep going here. So every mole of O2 is 22.4 liters. We can figure out how many liters of O2 we'd use. So if we use a half a mole of C8H18, which we know we're using because it's the limiting reactant, we're going to figure out how many liters of O2 would be used with it out of the 224 that were available. So that ends up being 140 liters of O2 used, not excess, used. Subtract for 224. So 224 liters were available. So we got 84 liters of excess. Not too tough there. All right, one more question. I'll do this one real quick. Got 100 grams octane at 250 degrees Celsius. So they're gonna burn 100 grams of octane, 100 grams of that at 250 degrees Celsius. The products are collected. So the products, CO2 and H2O. We're assuming there's no excess oxygen here. Collected in a 50-liter steel container. What would be the pressure in the container after the reaction is complete? Assuming the temperature must stay the same. So think about that. We know the volume of the container. We know the temperature of the container. If we want to know the pressure in it, we need to know how many moles are going to be in the container. And there's going to be moles of CO2, moles of H2O. There'll be a little bit more moles of H2O than CO2. So let's do a little strike. Say, I'm going to start this up here. We have 100 grams of C8H18. It is 114, yes, 114 per mole. Now we do a mole ratio for every 2 moles of C8H18 that are used in the reaction. We make 16 moles of CO2 gas, 18 moles of water vapor gas. It would be gas because we're at 250. So let's just add those together and say we make 34 moles of gas total. So that ends up being 14.9 moles of gas to be made. So if we burn 100 grams of C8H18, we make 14.9 moles of gas. We can plug that into PVNRT. Plug that in for N and solve for our pressure. I got a pressure there of 12.8 atmospheres. There's that.